Congratulations on getting through Unit 7. Now, as we approach the second unit in our topic series, we're going to look in section 8.1 on this thing called an error approximation. We know that with all the series we created in Unit 7, they were just approximations. So the question is, well, how can we estimate the error amongst them all? And today, let's just quickly take a look at our idea of an alternating series and talk about its remainder. Well, if you have a convergent alternating series, when you approximate the sum of that series by using only the first n terms, the error then will be less than or equal to the absolute value of the next term, or the nth plus 1 term. Just think about that for a sec. An alternating series, and then the remainder is the next term, the one you did not actually use. Okay? And if you're not too sure why, just think about some examples and you should be able to see that, yes, this would be the largest, or the error will be the less than or equal to that. Alright? Now, let's take a look at the actual example. So example number 1, I asked you to approximate this sum. Notice we have the sum of n equals to 1 to infinity. It's negative 1 to the power n plus 1, so that's the alternating part. And it's 1 over n factorial. So let's just go ahead and try to write out the terms. That's pretty straightforward. Just plug in the number n equals to 1, and then 2, and then 3, and then 4, and then 5, and then 6. Notice I use the approximate equal, not the equal sign. And if you were to do this, 2 factorial is 2, I think 3 factorial is 6, 4 factorial 24, 5 factorial 120, 6 factorial 720. You can plug this into your calculator to calculate what that will be. 1 minus a half plus a 6 minus 24th plus 1/20th minus 7/20ths. Ta-da! 0.63194. Okay? Now, the upper bound of the remainder. So, looking at the approximation, I said to you that the absolute value of the next term will be the remainder. So the next term will be the 7th term. So notice that the remainder will be less than or equal to the absolute value of the next term. Well, the next term I know is positive anyway, so I don't really need the absolute value sign, but I'll just show it to you anyways. And since that was 6 factorial here, it'd be 7 factorial. So what is that? 7 factorial. Well, I'll just write it like that. Okay? And what is the actual value here then? Well, once again, using your calculator, 1 divided by 7 factorial. Where's my factorial? Under probability number 4. Notice you get, whoa, so that's 4 decimal places, e to the negative 4. So that'd be 0.000198. So the remainder is less than or equal to that. Now, using that value, can you tell me the upper and lower bounds for the actual sum? Well, since I used the first 6 terms and I got the answer of 0.63194, that would be my lower bound. I know my series is the lowest at that, but the question I have for you is, what is the largest? Well, because I told you from example 2 the maximum remainder is 0.00198, then the upper bound really is just taking my value from example 1 and adding to it the remainder. And in this case, this is less than or equal to 0.6321429. Okay? So it's between these two values here. That one and that one. And those are my upper and lower bounds. Okay? Hope that makes sense. Sometimes they'll ask you questions like the following, where they say, just approximate, but make sure your error is less than 0.001. So here, they don't tell you how many terms. You have to figure out how many terms such that your approximation has an error that's less than 0.001. Okay, so how can we do that? Well, looking at this summation, once again, I'm going to ask us to just start writing down a few of the terms. Once again, it's alternating because of the -1 to the power of n. We'll start by plugging in n is 0, so that's just 1. We'll plug in n is 1, that I believe is 1/2. And then let's go ahead, that'd be 4 factorial, 6 factorial. Now I'm just writing these terms, I really don't know where to stop, but I should be able to calculate what these terms will be. Just curious what the terms 1 over 6 factorial, what is that? That's 0.001388. So notice 0.0013001, that's almost less than, so I probably need to keep that term. I'm curious what 1 divided by 8 factorial would be. And lo and behold, that's way, way less than 0.001. So really, I just need to cross that one out and stop right here. So I can use the first 4 terms now to approximate. So 1 minus 1/2 plus 1 divided by 4 factorial, which is 24, plus 1 divided by, oops, not plus, minus 1 divided by 6 factorial. And there you have it, the decimal of 0.54028. So this is approximately 0.5. Well, actually, that's not approximate. You know that's equal to 54028. Okay? So that is our approximation. Once again, that's an approximation, but going back to what you learned in section 7.6, can you use an elementary series to actually find the actual value of the series in example number 4? If you recognize the notation there for the summation, or if you can see that this is like 1, this is like x over 2 factorial, this is like, sorry, x squared, x to the power 4 over 4 factorial, this I believe will be x to the 6 over 6 factorial, and if you can say, ha ha ha, I know what that is, that must be the cosine series, or the series for cosine, you are correct. I would say then, what about the x value? What is the x value? So compare if you dare, but the x value I think just seems to be 1. So therefore this elementary series is the same thing as cos 1. And let's just plug in cos 1 and see what that value is. Wow, 0.54030. So very, very actually close to what our approximation was before. Okay, by the way, radians, okay, make sure you're in radian mode. So, what I want you to understand here is that for an alternating series remainder, the remainder is less than or equal to this messy thing. And this messy thing is really just the first unused term. Remember in the Taylor series representation, the next term will be x minus c, right, to the power of not n, but n plus 1. You're going to have the nth plus 1 derivative, and you'll evaluate this at c, and don't forget to divide by the factorial. So it's really the next term in the Taylor series, okay, or the first unused term. Now, here's a little twist. That works for an alternating series, but what about things that are not alternating? So what happens if you have a non-alternating series? Well, slightly different, yet mostly the same. We call it the Lagrange remainder, or the Taylor's theorem remainder. And notice the difference between the Lagrange and the alternating. The only difference occurs right here. What's Z? Where did that come from? Well, Z is the x value that's between x and c, inclusive, which makes the absolute value of that derivative a maximum. So when we looked at the alternating series, we knew that the derivative at c gave you the largest, or the maximum value. However, when it's non-alternating, we can't tell. So what we need to do is look in the interval between x and c. So let's say c, series is centered here. Let's pretend x is there. We have to look at every single value between, okay, including c and x, and see which one of these x values gives you the largest y value, and that's, or the maximum, and that's what we need to do. So you're going to hopefully find in here some sort of value that gives you the max, and that's what we use for our coefficient calculation. Okay, everything else is the same. So just like I said before, as in an alternating series remainder, the nth plus 1 term of the Taylor series is used. However, for the non-alternating one, using the Lagrange remainder, the derivative factor must be carefully chosen, and that's when I talk about this value of z. Okay, so if you turn the page, what I want you to understand is that that value of c must make the actual derivative evaluated there as the largest value possible. I told you it could be at the center, which is the c value. It could also be at the x value, or anywhere in between. Sometimes when you see sine and cosine values, you know what the maximum can be, so just say, hey, the maximum value of those must be 1, and you can use that. Alright, so let's try a few more examples here, and then we'll be done for today. If I asked you to estimate e squared using a Maclaurin polynomial of degree 10 for e to the x, this is really just a review from Unit 7. Hope you remember the e to the x function. 1 plus x squared over 2 plus x cubed over 3. Remember this one? By the way, I forgot my factorial signs. Oops. Because I want degree 10, I'm going to stop at the power of 10 factorial. I'm going to use this to estimate e to the power 2. That just means x is 2. So 1 plus 2 plus 2 squared over 2 plus 8, or 2 cubed over 3 factorial, plus all the way to t to the power 10 over 10 factorial. And I know you're dying to evaluate this yourself, so I will not let you do it. I'll just give you the response and the answer, 7.38899. Okay? Now, we know that's not the right answer, it's just an approximation. I know if you get a calculator, you can just type in e squared and figure out what it is. But let's use this Lagrange form of the remainder to actually estimate the accuracy of this sum. So let's see if we can bound how large the remainder will be. Okay. So, looking at the Lagrange remainder, I'll call that LR. From the previous page, it's really the absolute value of the nth plus 1 derivative evaluated at z. Remember? That's the max. So x minus c to the power n plus 1 all over n plus 1 factorial. Shall we deal with the hard part first? Yeah, let's do it. So the question is, how can we find this value, the maximum value of the derivative? Well, it's the next term. So really I'm looking for the 11th derivative. And the 11th derivative of e to the x, thankfully, is just e to the x. Now, remember, we're now looking for the values in the interval. Okay, the interval between what? Well, it's the interval between x and c. Our c value, since it's the Maclaurin polynomial, our c value must be 0. And I'm asking to estimate e squared, so the 2 is my x value. So through this interval, can you tell me where the maximum occurs for the function e to the x? And of course we know e to the x is increasing like this, so the maximum occurs at 2. So the maximum occurs when the z value equals to 2, since e to the x is an increasing function. An increasing function, we know the maximum occurs at the right endpoint. So therefore, what I should replace that green bit with is the value e squared, because I know that's the largest it could be. Our x value, once again, is 2, so it's 2. My C value, since this is in the Maclaurin series, is 0. We know this is the 11th power because n was 10 in the previous example, and we'll divide this by 11 factorial. And if you're curious what this is equal to, it's 0.000379. Okay? So the error is pretty small, actually, right? Not bad. Okay. You can try number 8. Okay. Same kind of idea. Notice it's the fifth derivative of x is 700 sine x. So I gave you the fifth derivative. And I told you the x value is 0.7. And it's in the convergence interval for the Fourier series centered at x equals 0. So notice this is like my c value, right? C equals to 0. Find an upper limit for the error when the fourth degree Taylor polynomial is used. So once again, since I used the fourth degree Taylor polynomial, my Lagrange multiplier, or not multiplier, Lagrange remainder will be the absolute value of the next one. So not the fourth degree, but the fifth degree. So I know it's going to be the fifth degree derivative, or the fifth derivative. X minus c. Now I know the x value is 0.7 and the c value is 0. And I know the power is going to be 5, and divide by 5 factorial. The question once again remains, what is the largest value of the fifth derivative at z? And since I told you the fifth derivative is 700 sine x, you should know that the maximum value of sine x is 1. So the maximum of the fifth derivative must be less than 700 times 1. Okay? So we can say that if this is equal to 700, that's 700 times 0.7 to the power 5 over 5 factorial, and that's just equal to 0.9804. Now, my question to you is this the best approximation to use? Well, I know this is a safe one, but is it the best? Probably not, because really what I said was we should look at some sort of interval, right? So what would the better answer have been? Well, the better answer would have been to look at what interval? The interval between 0 and 0.7. And for the sine function, what value or where in this interval will I get the largest value? Sine, I think, between 0 and 7. Remember the graph? Whee! Right? This is pi over 2, which is about 1.57. So between 0 and pi over 2, it's always increasing. So once again, the max would occur at the value of 0.7. So really, instead of using 700, I could have used, okay, f5z, could have been just the fifth derivative with the z value at 0.7. And that, I believe, if I were to calculate this, let's go ahead, 700 times sine of 0.7, I could have used 450.9 instead. And this would give me a better or a more accurate error bound. And in this case, if I were to now use this instead of the 700, you can calculate that yourself. So let's try. The Lagrange remainder would be 450.952 times 0.7 to the power of 5 divided by 5 factorial, which is 120.631596. 0.631596. So this would have been a better answer than the 0.9804, yet both are correct. Okay. I'm going to ask you to try example 9 on your own. I think it's quite straightforward. And then check your answer with me, and we'll be done and ready to do work in class. Ooh, decreasing function this time. Where does the max occur on a decreasing function? So once again, our interval in question is between 4 and 4.1. I would say that since the sixth derivative is decreasing, the max occurs when z equals to, not the right endpoint, but yes, the left endpoint. So therefore, the Lagrange remainder would be whatever the sixth derivative is evaluated at 4. The x value is 4.1. It's centered at 4. And then divide that by 6 factorial. So the sixth derivative at 4 times 0.1 to the power 6 over 6 factorial. There you go. We're done.